All right, if we can find our seats, we'll get started. Good morning and welcome to the session on preparing for Parker Solar Probe and Solar Orbiter, a coordinated science from the corona to the inner heliosphere. My name is Kelly Cork. I'm a scientist at the Smithsonian Astrophysical Observatory, and I am one of the co-chairs of the session along with Giannis and Nathan. So we're going to get started, and we have the distinct pleasure of welcoming Dr. Thomas Zurbuchen to talk about NASA's Parker Solar Probe and Solar Orbiter mission, discovering the secrets of our star. Thomas? Slide advance.
All right.
Get a yellow light too.
All right. Well, thanks for getting up so early, everybody. And I'm really glad to be talking here. Normally, I don't really give talks about missions because there's great directors that do in scientists at NASA that can do better jobs than I do to talk about this. Here, I made an exception just because I think this mission is such a crucial part of our overall portfolio. A portfolio, of course, that spans 105 missions all over both heliophysics, earth sciences, astrophysics, and of course planetary sciences as well, all the way from the Voyagers that are out there doing fundamental science to missions that are in our Earth environment looking at our changing planet. And of course, in heliophysics, a series of missions that are in boldface there that you heard yesterday that are ready to launch in the next year or two, depending on how things shake out. And of course, the Parker Solar Probe is the one there at the top that I'm going to spend most of my time on. First of all, what I wanted to point out is those are all the gentlemen missions were named after. I'd say if you counted 20 of them, all the way from people in the antique who made important measurements or had important discussions about the solar system, about the world around us, and also have provided deep insights that made them candidates to have missions named after them. But it never happened what happened here, which is a picture taken on October 3rd this year where Parker met Parker, right? The person that the spacecraft behind him there was named after actually met that spacecraft. So he, of course, is the first person who basically had the honor of having a spacecraft named after him. And so I just really feel, of course, that's deeply appropriate because of the fact that Parker here, taken in the 70s at his University of Chicago, did such fundamental work that basically everything that we work on today in heliophysics and also in plasma astrophysics, also in some of the planetary sciences actually is built upon. I mean, if you really look, we always talk about standing on the shoulders of giants. If you look where these ideas come from so often, you're going to end up citing an original paper by this guy. Of course, the paper that he wrote was in 1958, a paper that so many of you, of course, and I have used in classes, talked about it, derived on whiteboards and blackboards, over time, and basically really talked about the importance of, a transonic solar wind that really took off from the sun, went through a critical point, and became supersonic and omnipresent. That was critically important for understanding the atmosphere of the sun, but also with it, of course, a magnetic field that's carried out at this, what we call Parker, magnetic field shape, an Archimedean spiral pulled out that has its radial and also latitude dependency as predicted and confirmed by so many of our missions all over the solar system. Of course, the critical element, one of the critical elements, the story, by the way, of confirmation of Parker's 58 paper is multifaceted, like so often, with the Soviets at that point, doing important work. The Mariner 2 spacecraft really put it all to bed, so to say, because after its launch in April '62, Marcia Neugebauer, the JPL team, did measurements on the outside of the bow shock away from the Earth influence and basically show, just like Parker predicted, that not only the solar wind is supersonic, but it's always there. It's omnipresent. It's not an intermittent phenomenon. The sun is not burping, so to say, every once in a while, but it's really blowing that wind out in all directions, certainly in the ecliptic in this case, at all point. Of course, with Ulysses, we know that that statement is true in all directions. And so basically, shortly thereafter, actually even before the confirmation of the solar wind hypothesis, I would say, that Parker put out in his 58 paper, even before that, studies started pouring in, solar wind concepts all the way to 58 that were put together by science committees and then academy committees and then internal roadmaps and so forth. And basically what, and a top priority in actually surveys, especially a survey that really put it out there and really started talking about this. Of course, the challenge is that if you go that close to the sun, you have to learn to do more than just measure solar wind. The most important thing is you have to learn to survive that close to our star. And what that means is, of course, you have to protect yourself against the heat at the same time as making power. So you can actually not just be kind of a metal brick that flies by, but you can actually do amazing science. And even though in 58 a lot of the aspirational work was there, it's those kind of technologies that have to be happening at the right time. And the right time, of course, is now. The right time is when finally the Parker Solar Probe design, initially called, of course, Solar Probe Plus, was there. The story about that is amazing. I'm not going to tell it, perhaps others will, because it was one of those important stories of constraints being important for actually finding solutions. Constraints kind of taking some of the more complex, kind of closer mission concept off the table to replace it with something that actually can be done now, as opposed to the perfect solution tomorrow. Something that can be done now. If I could choose today, that's just me talking, Thomas Zurbuchen, the scientist, if I could choose today, and with the initial solar probe and the one we're doing now, and just basically say pick one, I would always pick the one we have right now. It is the better mission for where we are right now. But we had to come out of our hole that we were in over decades that basically said if we don't go within the critical point, it's not worth doing. We told each other. It's not true, of course, for many, many reasons that will come out. So the science, of course, is threefold that we're going to look at with this amazing mission, the flow of energy that heats and accelerates the corona and the solar wind. Of course, what we're realizing, this is an important question, not just for this star, but also for all the stars around us that we know have planets and where that kind of plasma environment is such a critical part to setting the environmental conditions on these stars, including atmospheres that, of course, we want to see and observe for the first time from space next year or the year afterwards. Determine the structure and dynamics of the plasma and magnetic fields as a source of the solar wind. What's really cool here, of course, is the multiscalar properties of that problem, where, of course, at the smallest scale, important kinetic processes are happening that we're observing in the magnetosphere and elsewhere, such as reconnection and so forth. Whereas, and actually with rocket experiments as well, even looking at the sun and otherwise. But at the largest scale, of course, having these kind of large-scale evolution of the magnetic field undergoing this transformative change on a time scale of decades. And so basically, both the spatial and the temporal scales interacting with each other through the important injection of time scales and spatial scales because of convection and the magnetic fields at that spatial scale. This is such an important problem that, frankly, at this moment in time, I consider one of the open problems that I hope will make a major dent in it or resolve. And then, of course, explore mechanisms that accelerate and transport energetic particles. One of the big questions out there that we're starting to make dents in, by looking at both the outer boundary of the heliosphere, but looking at kind of the biggest accelerator in our solar system, really understanding it there up front and personal, I think that will be one of the key breakthroughs that will come of it. Again, this is absolutely critically important, not just for heliophysics or solar physics. It's absolutely important for many other phenomena that are imaged, for example, by X-rays in the planetary world or in astrophysics. And so basically it's the Parker Solar Probe mission to touch the sun. Now when we talked about this in October, you may or may not know, this is one of the top 25 stories of all of NASA last year. And here's a little anecdote for you. I actually made my boss really angry about it because I get this, pretty sharply worded emails like, why didn't you tell me you're going to do this big story? And the answer is, well, look, I just told you it's going to be a local Chicago story. I told them. Basically, I felt the important thing is to celebrate that renaming at the place where Dr. Parker, of course, worked for many years, and do it at Chicago. I had no expectation that it would go much farther. Of course, I knew it's going to go farther when all of a sudden, as I was coming off the stage, I got messages on WhatsApp from Germany and Switzerland that said, you're on the news right now. So I was like, okay, this is going to be an international story. Of course, the issue is we totally had underpredicted. And so, I call this a good problem. You underestimate kind of the positive news that this makes. I think what did it is actually that inspirational quote, the mission to touch the sun, that of course Nikki and her team really developed together with the science team here. It's really inspiring. But that is, I would argue, kind of a key element of what is going to bring progress in the three areas that we see. The other one that I want to talk about is Solar Orbiter, which is really a good complementary mission that is going to the inner heliosphere and taking both in situ data but also remote sensing data at the level that is unprecedented. Of course, the US providing some instruments, but this being an ESA mission, this is a mission that will overlap significantly with Parker Solar Probe, most likely to be launched in 2020, I think Peck said yesterday. And so we look forward to getting it up there and really combining. What I also want to make sure is that you remember, of course, that and also in 2020 another kind of mission comes online, and that's one that's on the ground, which really is designed to measure magnetic fields, really the dark matter of the corona, right? Kind of where the energy sits in the corona and is basically observed from the ground. The reason I'm talking about those three together is to really challenge challenge you as a community to really see these three missions together as a solar corona inner heliosphere campaign. It's truly a historic campaign for which the science that we do is best exploited if we work together. And really it's important that the measurement that the DCAST is doing, the solar orbiter, kind of how the measurements happen there and what happens at Parker mesh together to really give us the important answers in science that we aspire. I would argue if we don't do that integration, we're really leaving kind of important science on the table that we should not. This is an opportunity for this community to really break through these boundaries of ignorance that we currently have in many of these questions and work together. So I'm really committed to work with you and with our partners to bring this together. I would argue we should do this actually a lot more deliberately than we have so far. So basically I just wanted, that's kind of my key message that I'd like to put out there, really to challenge and both the community and all of you. So I want to stop with this one. I mean, I couldn't be more excited. I look at pictures that come from the integration and test. As always, we're always worried until it finally works. That's just the job. Kind of if you have the job, I have 105 missions, so every problem. So it's kind of reading email in the morning, really takes almost a strong drink at times, It's like, but it's like okay. So, but of course, I really want to thank you, the science team, Nikki, and both the leadership and the engineering team around APL and everywhere that have really brought this to the doorstep of this historic achievement that hopefully will blast off into the sky next year. So this kind of avalanche of data starts coming in and we start addressing these questions. I want to stop here. Thanks so much.
Thank you. We have time for a question or two. Is there anything you'd like to ask?
Kelly?
Yes.
Yes. Thomas, I couldn't agree more that orbiter and probe with DKS are really going to create an SH community. Right? It's really a display of SH community. So we need a large community effort to, to realize the science. So we need a program. We need a GI program. We need some dedicated science funding in order to make it happen, in order to get out the science that we need to get out of these missions. What plans does NASA have for setting up such a program? And as you recall, the Cable survey said that we should have GI funding, a GI program for every mission.
Yeah, so I mean, remember, I'm not the, heliophysics division director, but we're committed to doing exactly, to putting the program together that supports this kind of initiative and do so in the most efficient and most effective way possible. And yes, so what exactly the name is of such a program, I don't want to go commit up here, right? But look, I mean, this is critical. We cannot miss that opportunity. And I think, if you have suggestions that, of the type that you're making, talk to PEC, talk to our team. I mean, my feeling is that early next year, as we go through to launch, this is the kind of activity we should be building. And yes, it should have consequences for how our program is aligned, but it also have consequences of how we do the science. I mean, both are critical. Thanks for the comment.
Ron?
I agree that DKS is essential to make sure we make that field, the complementary ways to go to the mission, but as important or more important to take the time.
Thanks. By the way, the one thing that is at the risk, the chart that I showed, is at the risk of understating the importance of other assets that are really critical. Kind of the way I think about it is, right, kind of you have a backbone of a campaign that is made out of firsts. But the one that you're mentioning is really critical, as are others that are out there and really have to provide both contextual and other information for that. So in no way did I mean to understate the importance of others. I just really feel that kind of what creates this historic opportunity is the kind of the coincidence of these three firsts at the same time, and together coalescing with the assets that are out there, including in situ and remote assets, well, we get the most important science. So in no way did I mean to imply that these others should not be included. But thanks for the comment, Ron.
Thank you, Thomas. Let's thank our speaker again. Next up is Dr. Nikki Fox, and she will talk to us about Parker Solar Probe.
Push the arrow. Okay. Good morning. Apologies for my late arrival. I forgot my badge and had to run all the way back up Canal Street, so I've done my steps this morning. Sorry, Thomas, for being late. And so it's my pleasure to give you the status update on Parker Solar Probe as we push forward to our launch next year. Oops, other way. There we go. So Thomas already talked about this, but I could not resist showing some of these pictures. So we are Parker Solar Probe, and we had the great honor in October of hosting Gene Parker at the Applied Physics Lab. He came to our SWG meeting, and myself and Thomas actually got to say, Parker, meet Parker. And so you see some great pictures of him addressing us and kind of kicking off our science working group. He was extremely humble. I will share with you one of the things that he said, which was, he turned to me and said, really what I did was so easy. I just wrote a paper. And he said, and I'm a theoretical physicist, so if you fly there and it turns out I'm wrong, I'll just write another paper. He said, however, if you get this engineering wrong, yeah, that's much more of a problem. He's like, you guys are doing way harder work than I ever did. So it was very sweet. Okay, so this is Parker Solar Probe on a slide. And Thomas has already briefed a lot of this, so I won't belabor the point, but he did a very nice job of talking about our three overarching science goals. I am delighted to say that we've had no changes in our science or our level 1 requirements, any significant changes in that, actually since phase A. So as we went into phase B, our level 1s have been pretty stable. Our launch, we are launching from Kennedy Kennedy next year. Our launch window opens July 31st. It's a 20-day launch window. Obviously, it's a planetary launch window because we need to have Venus for our first flyby. And we're launching on a Delta IV Heavy with an upper stage. We do our 24 orbits, so we have 24 flybys. Each time we fly past Venus, we step a little bit closer, so our perihelion drops. And so by the time we do our last perihelion, we're within 10 solar radii of the surface. We have a six-year, 11-month mission. During that time, we, as I said, 7 Venus flybys. We are moving at a blistering speed of 430,000 miles an hour, or 118 miles a second, which I still can't get my mind around. Our spacecraft, we still have, again, no big changes. We're 3 meters tall, 1 meter across on the bus. Our TPS, our heat shield that we love and cherish, is 2.3 meters across. So we're in the really hot, really exciting region of the corona, and our heat shield has to withstand temperatures of 1400 degrees Celsius or 2500 degrees Fahrenheit, while most of the instruments are basking in a very comfortable room temperature on the body of the spacecraft. I'm going to go through the instruments one at a time, but I'm pleased to say all instruments are integrated onto the spacecraft. And so I will start looking at the anti-ram facing side of the spacecraft. But the bravest little instrument on the spacecraft, SPC, our solar probe cup, is now integrated. It was a little bit late coming in, but we are delighted to see it sitting on the spacecraft. And that is one that does not bask in the shade of the heat shield, but sticks out around the side and is in the full solar environment. You also see our solar array cooling system there. For those of you who don't know, that is a unique design. This is the first time that we've flown solar panels that are actively cooled. They have water flowing through them, just like veins through your fingers. They have water flowing through those solar wings that keep them cool, and those radiators you see around the edge of the thing that holds our heat shield are actually getting rid of the heat from those solar wings. You also see SPAN B, that is an electrostatic analyzer looking at electrons, and its sister instrument is on the other side. SPAN A plus looks at electrons and ions, and together they have a full 360-degree field of view, so we can see the electrons coming from all directions. Let's see, the field's antenna, we have 4 whips that stick out, again, in the full environment, and they are joined by a suite of 3 magnetometers on the back, two flux gates and a search coil, and together they make up the field suite, and the PI for that is Stuart Viall. Should have noted the PI for the suite, which is very hard to say, is Justine Casper. The ESIS suite, epi-high, epi-low, are looking at our high-energy particles, things associated with shocks, CMEs, flares, anything that's really exciting and transient on the sun. PI is Dave McComas. And last but certainly not least, our white light imager that is doing fairly unique imaging, taking images of the solar wind, not images of the sun, allowing us to really put into context all of our in-situ measurements. PI for that is Ross Howard. So our timeline, we went through system integration review last year. We started INT in August of 2016. We had our KDP in July of 16, and we went through our launch and early operations review. All of our instruments have gone through their pre-environment and pre-ship reviews. That took about a year to get through every subset and every piece of them. And then we just finished our mission PER, our pre-environmental review. We're on schedule right now to do our pre-ship review in March of next year, and then ship to the Cape shortly thereafter. Ready to, our next stop is our Delta IV Heavy. Our first perihelion, so we don't waste any time. We launch July, August of 2018. Just 3 months later, we are at our first perihelion, so there's a lot of work going to go on in those first 3 months. 6 weeks after launch is our first encounter with Venus, and then 6 weeks after that, we are in the corona, and I don't think anyone could be more excited than our science team about that first perihelion. And then we do, another 23 orbits, 21 orbits, and then orbit 22 we get within 10 solar radii. So a lot of excitement going on there. I love rockets. I just wanted to show you our boosters because they're so impressive. We have three of these Delta IV heavies strapped together. I particularly love the picture in the middle because it looks like it's kind of trying to hide in the trees. Probably need a few more palm trees if that's going to happen. But there it is. It came in on the ship into Kennedy, off the ship, and was put into the horizontal integration facility just a couple of days before the hurricane. And so I was there as they were evacuating, and they promised me, no, we'll be fine, don't worry, we might just get a little bit of water under the doors, but we've withstood way more than this, and pleased to report they did in fact survive the hurricane. So our boosters are in-house. Some highlights from integration and test. I apologize about the cheesy music, but video is worth lots and lots of pictures, so I'm just going to talk you through. So here we are. This is from a while ago. This is when we did our primary structure assembly. I love this because you see just how small that bus is. We then put in our flight harness, which was developed and integrated beforehand and then dropped into the structure. This was when Solar Probe started to really look like Solar Probe, when we put her top deck on, and then suddenly she grew into a 3-meter tall spacecraft. Our high gain antenna, which was integrated onto the spacecraft. Very important for us to get our data back. The most terrifying thing I've ever seen, somebody swinging that spacecraft held by a couple of straps. That was our magnetic field swing test for fields and sweep. Here go the solar panels onto the side. Most of the time you'll see them, they're completely covered, so we protect those solar panels. And then this is doing our final bonding of the heat shield. Must be an interesting job laying across the top of that for many hours. There is the flight heat shield, and this one looks like they're having some kind of seance, but they're actually putting the final, bonding the top sheet on. And here we are lowering the heat shield onto the spacecraft. So the heat shield remained on while we did a lot of the system testing. The heat shield has now come off again. The flight heat shield is actually it just went into thermal vac at Goddard into the big chamber last Wednesday. And I should have included a picture because it was quite amazing seeing this little tiny heat shield so high up in the air and then going into this huge test. We actually will lift the entire spacecraft on December 26th. So anyone who's around Goddard, it's probably worth shaking off your Christmas dinner and coming to see that. Okay, so where are we recently? So you just saw a shot of the TPS. I included this because any future pictures that you will see until we actually get encapsulated will not have a heat shield on. But there is the heat shield sitting pretty on top of the spacecraft, and just especially for the SPC team, a nice picture of SPC finally on the spacecraft. That's the one on the far right, looking a little bit like a mini Solar Probe, actually. We hadn't realized just how much it was going to look like Solar Probe, sticking out the side there. So our recent accomplishments, I just pulled some things that we'd done in November. So as I mentioned, we have shipped from APL. We are now at Goddard for our final integration and test before we go to the Cape. So we did the observatory level acoustic test. We actually did the vibe, all the vibe testing was done at APL. So the next thing we did was the system level acoustic testing. The one that looks like a Halloween image with the purple at the bottom there, we successfully tested all of the solar arrays, and that was done with a very thin kind of knife edge laser so that we could actually stimulate each row of cells and make sure that they were working perfectly. We did a shock test. Again, that's kind of frightening when you drop the spacecraft, but we did do that. We tested the set nuts, and we actually tested what would happen to the spacecraft when it gets shocked in that fairing. And then we also, after doing all that acoustic testing, we then had to make sure that all the components were still working and deploying. So what you're seeing there is a walkout of the mag boom. So lots of exciting stuff going on. Getting involved, I just wanted to put up this slide kind of as a sort of takeaway message. So we did publish a series of papers about the instruments and about the mission, and they are all published in Space Science Reviews, so you can go and pull those. They all have open access. We do have a science gateway where we will actually, right now there's not a lot on there apart from things that are good for mission planning, so you can go and find a detailed look at our trajectory on there. But please, you can sign up there, and that's where all the data will be available from. Obviously looking out for PSP-related sessions, and you're welcome to come to a science group meeting. Publishing predictions, theories. Get excited. I'm excited, can you tell? Get excited. It's an awesome mission. Sort of jumping in on Spiro's question about the ground-based support, we're very much hoping that we can work with NSF to do a campaign where we actually can have support for the ground-based, because there are a lot of those perihelion passes that are actually visible from Earth. And so more than just Solar Orbiter, Solar Probe, and DKIST, but we've also started working under the leadership of Tim Bastian with the whole ground-based community to be able to do that. And so I'm going to leave you, because I can, with our mission trailer.
NASA's Parker Solar Probe mission is about to embark on a historic journey to our very own star, the Sun. Named for Dr. Eugene N. Parker, whose contributions have revolutionized our understanding of the Sun, Parker Solar Probe will usher in a new era of exploration. It's a mission of extremes. The spacecraft will plunge through the Sun's atmosphere, called the corona, and fly closer to the Sun's surface than any spacecraft in history. More than 7 times closer. The Sun's surface is hot, at temperatures exceeding 10,000 degrees Fahrenheit. But the real surprise is, its atmosphere is even hotter, 300 times hotter. Facing the corona's brutal heat and radiation conditions, Parker Solar Probe will finally provide answers to some of the most important questions about how our Sun works. As Parker Solar Probe speeds around the Sun making these measurements, it's moving at over 430,000 miles per hour. That's like traveling from New York to Tokyo in less than a minute. This mission is the culmination of 60 years' work by the best and brightest scientific and engineering minds. Today, our technology will let us achieve our dreams, to reveal the secrets of the corona and our Sun, and to one day help better protect technology from the threats of space weather. In 2018, we will launch Parker Solar Probe, humanity's first mission to touch the Sun.
Thank you, Nikki. Okay, we probably have time for one question. Any questions for Nikki? 0.
Will Gene Parker come to the launch?
He is invited, and he is hoping to come, and I will, when he came to APL, as you know, his whole family came with him. It was great. And so I think we're just going to get a bus for his entire family and bring him down. So he is very much hoping to come to the launch, yeah. Yeah.
All right, let's thank our speaker again. Thank you, Nikki, for sharing the excitement. So our next speaker is Dr. Daniel Mueller, talking about another exciting mission to the Sun, ESA's Solar Orbiter mission. Nikki, the solar probe just does not want to leave the screen. There we go.
Good morning. So I would like to start with an apology. This presentation will only have 2 movies and no special effects. It'll be kind of like going back to the 80s and the analog age, but nevertheless, I hope I can give you a brief overview over Solar Orbiter, which is a joint endeavor of the European Space Agency, ESA, and NASA. And our goal is to contribute to exploring the connection between Sun and Heliosphere. Okay, so just in a cartoon, what Solar Orbiter will do, it has already been motivated by Thomas and Nikki. The idea is inherently to connect the sun to processes taking place in the heliosphere, and Solar Orbiter specifically will do remote sensing observations with its 6 remote sensing instruments, and then try to connect phenomena observed in situ by the 4 in situ instruments to their sources on the sun. So in this cartoon, you can see a flare happening on the solar surface, which we will image in both UV and X-rays. We'll also take magnetic field data on the surface, and then we will be able to measure radio bursts with the RPW instruments and measure energetic particles, both electrons and ions, in the solar wind. So the science objectives of the mission, the overarching question is really how the sun creates and controls the magnetic plasma bubble around it, the heliosphere, and the associated question of what really makes the solar dynamo tick. And we sort of subdivided the top-level objective into 4 themes. The first theme is about the drivers of solar wind, both fast and slow and mixed, and the origin of the magnetic field in the solar corona. The second question is about how solar transients imply changes in the heliosphere. This is something that has already been the trail has been blazed by the stereo mission. Question 3 is about SEPs, and question 4 is about the long-standing question about how does the solar dynamo actually work, and in what way does it influence changes in the heliosphere. And the question to the origin, the physical origin of the solar dynamo could most likely be deciphered by looking at the poles of the sun, and this is what Solar Orbiter will do. We wrote a mission overview paper a few years back in Solar Physics where this is sort of described in more detail. Okay, so this is the sort of mission profile in one slide. After launch, we'll get into an elliptic orbit. We'll use Venus and Earth gravity assist to gradually crank up the inclination out of the ecliptic plane. With every flyby, we'll gain a few degrees, and initially we'll use these flybys also to reduce the perihelion distance to just within Mercury's orbit. It's planned for a 10-year mission, as Thomas alluded to it already. Until recently, we planned to launch in February 19. All the instruments have either been delivered or are essentially ready for delivery. Unfortunately, the integration of the spacecraft bus is proceeding, but not quite at the schedule we would need to make February 19. So for the time being, I wrote February 20. This is something to be agreed on the headquarters level between 2 agencies. The good part about it is that if we do launch at that date, it is essentially the same trajectory as for February 19, just minus a 1-year parking orbit, and I'll show a movie about that later on. So in that case, we have a cruise phase of just 1.8 years, which is the shortest cruise phase of all options we have studied so far. This would be followed by a nominal mission that could then hopefully be extended pending successful reaching the science objectives in the nominal mission. As I said, we'll get out of the ecliptic plane. In the nominal mission, we'll get until up to about 24 degrees, and this will, towards the end of the mission, when solar probe will get to its closest perihelia, we'll get to the highest inclination of around 33, 34 degrees. And another nice asset of getting close to the sun is that you will have periods where you will essentially co-rotate with the sun, and you can observe features on the sun from longer than you can from the ground. And as Nikki has pointed out, Solar Probe is clearly an encounter mission, and so is Solar Orbiter. We'll focus really on joint observations between all 10 instruments around periods of the orbit where they are most exciting, because both are deep space missions and we can't get as much data down as we can from missions close to Earth. So we'll focus on windows typically centered around the extrema in latitude, north and southern polar passes, and perihelion, of course. Okay, so these are plots for the latitude and distance as a function of time. As you can see, for the latitude, it takes a few years to really get to where you really want to be to do polar science. But in terms of In terms of perihelion distance, already 2 years after launch, we'll get within 0.3 AU, which provides really exciting close-in science early on in the mission. Okay, and plotted in different coordinates. These are the same curves, just plotted in distance as a function of latitude. And you can see that there's this knot where you pass by Venus and crank up the inclination. And in blue, I've indicated the northern polar passes, in green, the southern polar passes, and in red, the perihelion windows. So we'll get a pretty good coverage with the remote sensing instruments. The in situ instruments will be operating essentially around the orbit. And scientifically, and this is sort of the project scientist talking, we'll try everything we can to also get synoptic data of some remote sensing instruments outside these windows. But clearly, this is a question we can only really address once we get launched. Okay, so these are a few pictures from our flight model integration taking place at Airbus UK in Stevenage. You see in the middle the core structure of the spacecraft, which has a central cylinder, the launcher interface here at the bottom. And there are sort of two panels shown here. This is the payload panel where most of the remote sensing instruments are sitting, and also electronics boxes of in situ instruments. And here is a very busy communications panel with lots of electronics and onboard memory. Okay, we have solar arrays that are not quite as super special as the ones of Solar Probe, but nevertheless they're quite neat. The technology is inherited from the Mercury Bepi-Colombo mission, but they've been custom tailored to our needs. You can see here we added stray light shields to make sure that the yolks of the solar arrays don't reflect any stray light into the aperture of the sensitive heliospheric imager that Russ and colleagues are building at NREL, or have built at NREL. And also to meet the stringent electromagnetic cleanliness requirements of the in situ instruments, we've made an extra effort to cover the backside of the solar arrays in conductive foil, so that makes them look a bit stealth-like. This is our heat shield. It is a carbon fiber structure on which several layers of thin titanium foil are placed, and the topmost of which is surface treated to be very chemically inert. You can see sliding doors for most of the remote sensing instruments that will be peeping through the heat shield and protected from the sun's intense heat. And the silvery disk here is a beryllium window, which is the entrance window for the X-ray imager. This is a close-up of the instrument panel, the -Y panel. You can see the polarimetric and heliospheric imager here. The inner coronagraph MET is here, and in this place, the UV imager has been integrated now. You can see the UV spectral imager SPICE here, and then a bunch of electronics boxes all around. Once assembled, this is what it will roughly look like. The solar arrays will be tiltable, so we can adjust the temperature to make sure they are always in a safe operating range as we get close to the sun. And most of the in situ instruments are located on the boom in the shadow of the spacecraft, and two are actually looking through edges or indentations in the edges of the heat shield. And then we have very long radio antennas that are sticking out into the solar wind. Okay, I don't have time to go through the entire payload, unfortunately. I would say all instrument teams are represented at this meeting either by their PIs or other representatives, so if you have detailed questions, come and find any of these colleagues or myself after the talk, if you have any specific questions. I'll have 1.5 slides on the science to come back to the reason why we are doing this. This is really about trying to find out how the sun keeps this cyclic behavior going and how does this manifest in the heliosphere. This is a plot from at Owens. It shows the sunspot numbers for the last 5 solar cycles and overplotted the total heliospheric open flux. You can see a number of things. One is the solar cycle amplitude varies, and we still don't really know what drives the absolute amplitude. You can also see that the cycle length varies from 11 -2 to 11 +2 roughly years. And honestly, after many years, we still can't really describe or predict the solar activity cycle more than quantitatively. Okay, this is my solar orbiter in one slide. It has the 4 themes. I'll be quick here. This is about the solar wind, and this alludes to the comment that Spiro raised earlier. We'll need good modelers to either prove or disprove Spiro's idea of what drives the intermittent solar wind close to the open-closed field boundaries. And clearly, we need to have people write more papers about how this actually works. We have the theme of solar transients with a red line here that shows us where a solar orbiter will be going in a time elongation plot. And we have SEPs where clearly there's different competing mechanisms for the acceleration of the energetic particles that we hopefully can shed some light on. And then the question about the solar dynamo will get to the far side and to higher latitudes. It both help for helioseismology. If you do global helioseismology, it will reduce the leakage effects in your analysis. If you do local helioseismology, you can probe deeper layers, and ideally, we'll also be able to observe flow patterns close to the solar poles. Okay, and this is a slide on the geometry in heliocentric Earth coordinates. You see the sun here and the Earth here, and this is just to show you that we have a lot of different viewing opportunities. We'll have quadrature with Earth, we have Parker spiral alignments with Earth, and we have alignments in different ways with Parker Solar Probe, and many more opportunities that are worth exploring. Okay, so finally on the synergy, I hope that I could show you that Solar Orbiter has a relatively well-defined unique orbit in terms of distance, inclination, and longitude. It has a comprehensive payload suite. It is by its nature limited in telemetry because it goes far away from the sun. It's highly complementary to Solar Probe, which has in a way even more unique orbit because it gets so much closer into the sun. But also, like Solar Orbiter, it's an encounter mission with limited telemetry, especially when you compare with the data that can be brought down by SDO or produced by telescopes like DKIST. But those are limited to the Sun-Earth line. And maybe just one thing to point out is high spatial resolution comes with, of course, at a price, so you can only cover small parts of the solar disk. This is, for example, the VBI instrument of DKIST. Here it's still called ATST. And the black quadrangle is the Phi high-resolution telescope, and the big one is the full-disk telescope. And so in summary, Solar Orbiter will do its part to be part of the big new heliospheric observatory that Parker Solar Probe, Solar Orbiter, DKIST, and hopefully also SDO will providing. We will have unique new views of the sun, great opportunities for joint science. The engineering teams are doing their best to integrate the instruments as quickly as they can. And we hope that we'll be ready to launch for February 20. And this is a mission that's really been designed by this community and for this community. If you have more ideas and better ideas on how to make the best out of both missions, please get in touch. Thank you very much.
So we have time for one quick question. Anyone? Let's try someone a bit listening today. Spiro, we love you, but.
Are we coordinating the remote sensing windows of Solar Orbiter with the Parker Solar Probe orbit to make sure it's bite-sized?
Well, absolutely. And as you might be aware, we have a workshop coming up in March between the Probe, Orbiter, and DKIST communities to define, let's say, critical early science. Of course, we can only really nail down individual windows once we have launched. But clearly, the idea is that we want to make the most out of both missions and enable science that we couldn't do any other way. I mean, clearly, each mission has their own, let's say, level 1 requirements in NASA terms. So clearly, we can't write anything that is dependent on another mission on paper, but clearly, in terms of doing the science, this is something that we will absolutely do.
All right, let's thank our speaker again. Next up, it's my pleasure to introduce Dr. David McComas, who will talk to us about Parker Solar Probe and the history of how we got to this amazing mission.
Great, thank you. Okay, good morning. I'd like to thank the conveners for the invitation to talk about the history of Parker Solar Probe. I think I was asked to do this because I led the science technology definition team for the last 2 studies, which you can see here, but that's really just the end of the story. The story goes back, and I'll recount this story in brief, but it goes back for a very long ways in the history of trying to get a mission that would go very, very close to the sun. It's been studied a number of times. There have been various reports. There were various false starts and other things, and I'll try to quickly go through all of that. So it really came out of the very first idea for it, goes all the way back to the same year that Gene Parker wrote his famous paper, was also the year and in fact the month that NASA was founded, October 1958, when the Space Studies Board Committee on Physics of Particles and Fields in Space, chaired by Simpson and Van Allen, wrote an interim report. It had a bunch of different recommendations. One of the recommendations was for future missions that the new agency would do. One of those was for a spacecraft to go inside the orbit of Mercury to directly measure the near-sun particles and fields. And so that was the challenge. It's interesting if you go back to this report, I think all of these other suggestions I think have now been done with the exception of the solar probe, which we'll be doing next year. So early on, 62, and Thomas already mentioned this, Mariner 2 basically proved that Parker's basic idea was right. There was this continuous outflow of the corona into interplanetary space, the solar wind, supersonic expansion. Also pretty early on, by the mid-70s, there was the Helios Project in which there were 2 spacecraft that flew actually pretty close to the sun, 0.3 AU. Those are still the closest measurements that have been taken in situ. That's still a really unique data set. But one of the things that we learned from the Helios mission was that 60 AU wasn't close enough. There was already a lot of processing of the solar wind by the time you got to those distances, and so you really do need to get much closer than that. At basically the same time, there were technologies that were being developed for other purposes that became available to NASA for heat shields. And so around the mid-70s, there were heat shield technologies that it looked like you could get much, much closer to the sun. And this led to a workshop at Caltech, 1978. The workshop, the group examined objectives achievable by a solar probe that could go all the way into 4 solar radii and basically directly sample the corona. That led to a star probe study that would be instrumented to study coronal heating, solar wind acceleration, production of energetic particles. That all sounds pretty familiar for what we're doing right now today. Also, interestingly, included gravitational and general relativity experiments as part of that. And so that was the first major study that was really talking directly about a solar probe to go into 4 solar radii. The design evolved some. There was a NRC CSSP report in '85 that recommended in situ measurements, solar and plasma, electric and magnetic fields, energetic particles, again to 4 solar radii. There was a major study, the first science definition team. Bill Feldman chaired that, 1988. That was only in situ measurements. And then there was quite a bit of work, mostly at JPL, on the engineering and mission design. That extended throughout the later 80s and the 1990s. That basically evolved from a large conical heat shield, which was the mainstay of how you would get to 4 solar radii, to a different design for the high gain antenna. And you can see that here. These were the earlier studies. These were what I like to call the Dunce Cap design of the heat shield. Of course, you have this very high inclination angle, so you're radiating a lot of heat to space. This was one of the later sets of designs at JPL in which they thought you could actually have a similar, not a similar shape, but a similar steep angle, but then use the inside of the heat shield as a reflector in order to send the radio waves back to Earth, and so that was part of the telemetry system. These were also much smaller. So this was the evolution from 82 to 99, basically. And those were the 2 basic ideas for how you got into 4 solar radii. Okay, then of course, in our field, sometimes politics gets involved in missions. I know everybody's shocked to hear that, but it does. And while Bill Clinton was in the White House, there was a Russian policy that encouraged economic and technological cooperation in space, and in 1994 the Fire and Ice missions were conceived to send two spacecraft, into the Sun, a solar probe type pair of spacecraft, and also a spacecraft out of Pluto. It was a very aggressive fire program. Was going to have two spacecraft launched together on a Russian Proton launch vehicle, a U.S. spacecraft that would be in a 4x8 RS, elliptical polar orbit, and the Russian spacecraft would be in a 10x20. So not just going in for a short period, but spending a tremendous amount of time in close. However, after the loss of Mars 96 probe, Russia curtailed some of their robotic space flight activities, and basically this mission was abandoned. After that, there was sort of an ad hoc committee that Ian Axford led. It was convened to define a minimum solar mission. What was the least you would do to have a solar probe? It was very minimally instrumented. And it was interesting because basically the community, when they looked at this mission, wasn't very engaged in it, wasn't very supportive of it, and it kind of lost the base of support from the science community because the instrumentation was so minimal. Okay, and then finally, we got to a real mission, an AO, in 1996. George Gleckler led a definition team that recommended a PI-led mission that would have both in situ and remote sensing. That was a report that came out in 1999. NASA actually released an AO in 99, and in 2000, the community submitted multiple proposals. I led one of those proposals. They were for PI missions to do the full solar probe. However, in 2001, solar probe was shifted from the Outer Planets mission line, basically at JPL, to NASA's new Living with a Star program. And in 2002, the investigations that had written proposals and submitted those were basically returned to the PIs. That AO was canceled, and the proposals were returned. So it was a false start. All of that brings us up to what I think of as the present time. The driving force behind all of this, with all these false starts and all these studies that didn't really go anywhere, was that the science was so compelling. And so the science continued to be at the top of the list over these 60 years. In 2003, the NRC Decadal Survey called again for a solar probe as soon as possible. NASA's 2005 roadmap basically called for a flagship as the highest priority for new resources. And so the solar probe science wouldn't go away, even though there were many attempts to try to do a mission that fell through and didn't work out. And it was really the driving science is why we had to keep conceiving and reconceiving the mission. So that leads us to what I call the modern era. In 2002, the mission design shifted from JPL to APL. APL had some new ideas about how to do things, and I'll get to that. A new science and technology definition team was impaneled by NASA for the study. The mission that emerged from this study, the 2005 report, was very similar to the last couple studies for full mission. That is, you'd go out to Jupiter, you'd have a gravity assist, and you'd go into a solar polar orbit. You'd have to have RTGs in order to power the spacecraft all the way out at 5 AU. You drop into 4 RS from the center of the sun, leave aphelion out at about 5 AU, and you'd go in a couple times, actually only 2 orbits. This tall Dunce Cap conical heat shield, carbon-carbon heat shield, an integrated payload comprising both in situ and remote sensing. And so this mission had a baseline mission. It only provided 2 brief solar encounters. They were roughly 5 years apart. And actually the minimum mission was just 1 flyby in very close. And so this STTT report was published in September 2005. We were all very hopeful that that would lead finally to a mission. We published the science case for that and the review of geophysics in 2007. Got the cover of the reviews of geophysics. These were the people involved in the STDT report, the scientists who were involved in the STDT report. And so we tried to make a compelling case for the science, for the broader science community. We're hoping we were headed for an AO, but the cost that came back associated with this was deemed to be too high. Then a really interesting thing happened. SMD came back to us and said, and Thomas was talking about this disruption. SMD came back and basically said, tell you what, if you can find some way to retain the core science, cut about 1/3 of the cost out, and do it without RTGs, there's a really good chance that we'll find a way to fly this for the community. That was really disruptive, and the immediate response was sort of, that almost isn't possible. You know, we're good scientists and engineers, we looked at the mission, we're pretty sure we can't do that. However, by agreement that Dick Fisher and I had when we put together the STDT and the study that I just described, I said to Dick, hey Dick, let's keep this, this STDT formally impaneled in case things come up in the future and we need to respond to them. If you need a little Delta study or something on how to do it, why don't we just keep this in so you don't have to go through the process of re-impaneling? And so he said that was a great idea. We kept it in place. Oops, sorry. He basically then gave me a call and said, well, it's not a small change, but we've been asked to make a change, and this is what it looks like. Do you think there's any chance? I said, well, let's get the band back together and see what happens. And so we met again as an STDT. We reactivated to carry out the second study with the APL engineering support. And that led to this shockingly different mission, a mission in which instead of going out to Jupiter, going in and plunging into 4 solar radii, we would go over and over and over again, and by using Venus gravity assists, we would move progressively the perihelion down until we got inside of 10 solar radii to the center of the Sun, 9 solar radii from the surface. It's a really clever idea, and basically ended up giving you a lot of time where you spent in close to the Sun. You didn't get as close as 4RS, but you spent a lot more time inside of 10 and 20 solar radii. And so this was actually a solution. It meant you could get rid of the Dunce Cap and go to a much more standard flat heat shield. It's still complicated, and you still have, as Nikki was talking about, you still have to dump the heat, and so there's basically a radiator with water running through it so that you can dump the heat out the sides. So it's not easy, but it's not as hard as the Dunce Cap version because you're not going in as close. And I would say, and I was mentioning this to Thomas just before the session started, I personally think that kind of the big step in making the decision that we could do this came out of a paper that was being worked on basically right at that time, Zhao and Zurbuchen, which showed that you could actually see not just in the low latitudes in the ecliptic plane, you wouldn't just see the slow solar wind, but you would actually see coronal hole solar wind. They were using heavy ions in the solar wind in order to show when you could see fast flows from polar coronal holes, from low latitude coronal holes. And basically this paper showed that at all years, depending on the solar cycle, it varied, but even across all parts of the solar cycle, you'd be able to sample coronal hole flows down in the ecliptic plane. And that, for me, was sort of the thing that turned us over. And we said, gee, we don't really have to go over the poles to be guaranteed to see coronal hole wind. We'll sample all types of solar wind, even down at low latitudes. And so this kind of tipped us over, and we'll have tens of % of each of ICME's coronal hole and streamer belt type flows, even staying down in the ecliptic plane and using Venus to grind our way in. We also get hundreds of hours of each of these sorts of things inside of 20 RS. And so basically, the STDT concluded that it achieves all the traditional solar probe science objectives. It fits within the constraints, so it was flyable in the near future, was significantly cheaper, and got rid of RTGs and all those other things. Thermal protection system no longer had to handle 3,000 suns of heat, but something like 500 suns of heat. So it retired the previously highest risk item. It allowed for complete measurements and allowed for us to have a flyby mission to progressively move closer and produce statistical survey of the corona, allowed extensive simultaneous remote observations, and now observations with solar orbiter, as you've heard this morning. And would have an extended mission instead of just 1 or 2 quick flybys, would be able to have, I think, a very long extended mission with 4 close flybys per year. So a lot of pluses, something that we really felt was a much better mission than the mission that we'd been studying for the decades before that. And so in preparing for this talk, I went back and looked through a bunch of my old emails. I found this one. I just have to read this for you. So this is from an email I sent about 10 years ago. This is November 30th, 2007 to the STDT. It says, "Dear STDT members, thanks to all for making it such a great meeting this week. I'm really delighted with the mission that Andy, Jim, and Yang Ping and all the other APL folks have come up with." This is Andy Dantzler, who sadly is no longer with us. Jim Kinnison and Yang Ping Gao. Actually, Yang Ping is the person who came up with this really innovative idea to use the multiple Venus flybys that sort of tipped over the whole mission concept. Personally, with about 20 passes, 1,000 hours inside 20 RS, as opposed to less than 100, I like this mission much better than that in our 2005 report. Really appreciate how everybody pulled together to make the very limited compromises we need to make and form such a strong consensus. Now we need to follow through. There's a bunch of stuff we had to do. Anyhow, using our new name for the first time, Go Solar Probe Plus. And so this was basically 10 years ago today, almost, that we'd moved over to this new mission design. That led to the STDT report, which you've seen, July 2008. Gene Parker was not part of the STDT, but he actually wrote the foreword for it, and that led to the 2010 Solar Probe Plus AO. I put this in the wrong place, sorry. So this is Gene Parker's foreword for the study, and then the rest, as they say, is history. So launching 31 July 2018 Parker Solar Probe. Thank you very much.
Thank you, Dave. Do we have any questions for Dave? Ed?
Just, can you articulate the trade space between getting within 6 solar radii and the trade of having this extended observational period at a larger distance? How those discussions sort of happened historically? Because it seemed like there was a big driver early on that 6 solar radii was kind of a critical number, and then that was relaxed. So what was the interaction? Were there papers there that kind of...
It was an interesting discussion in the science and technology definition team, and I think one of the really strong drivers, besides the paper that I showed, which was another one of the strong drivers, was that we all came to understand that the solar wind and energetic particle environment is so variable in the solar wind and probably certainly therefore also close to the sun. And while going in closer is certainly better, the chances of seeing any particular thing was smaller when you didn't have very many samples. And we realized that having something where you'd have lots of samples and lots of opportunity to see the variability of the solar wind and energetic particle environment had huge advantages for the community. And so I think in many ways it was kind of an understanding that you weren't taking measurements of a stable system, but of a system that could offer you almost anything. And having all of these samples and grinding in closer and closer over time was just a huge plus for us.
Well, thank you so much.
Thank you.
Yeah, thank you. All right, let's thank our speaker again. Thank you, Dave. All right, next up is Dr. Nikki Viall, and she will be talking to us about combining remote and in situ observations with MHD models to really understand the slow solar wind.
All right, hello everybody. I'm going to start with a prediction, Nikki Fox. Prediction for Parker Solar Probe. There is no such thing as the steady solar wind. That's what I think we're going to find. What I'm showing here is a cartoon that Nancy Crooker drew 20 years ago of a crossing that she observed of the heliospheric current sheet. And I've got a quote here from their abstract that the observations at the heliospheric current sheet preclude a single wavy current sheet interpretation. Therefore, they interpreted the observations as a series of small-scale intertwined flux ropes. Now, this has since been confirmed at the heliospheric current sheet by a plethora of observations, both remote and in situ. People like Neil Sheely have seen this magnetic reconnection occurring at the sun at the heliospheric current sheet. Many people have seen this in situ near the heliospheric current sheet, including ourselves. But the question is, are these just transients injected on top of an otherwise steady solar wind, or are these in fact the fundamental building blocks of the solar wind? As you can see by my opening sentence here, I believe it's the latter. I believe these are the fundamental building blocks of the solar wind, and that's what we're going to find. Now, the key, though, is that the observations currently are really pushing the limits of the instrumentation. And so that's why we need Parker Solar Probe and Solar Orbiter. All right, I'm going to show some examples here. The question of whether these are just transients that happen at the heliospheric current sheet or whether they are fundamental building blocks really requires thinking about where can magnetic reconnection occur. Is it just a current sheet phenomena, or can it also occur at pseudostreamers, complex S-web structures, in which case it could be a universal injection of plasma throughout the heliosphere. So I'm going to focus on this event, August 2008. We have, do I have a pointer? No? Yes.
Pointer up there.
Pointer. Ah, right. Okay, so what's interesting about this time period, there's a pseudostreamer up here, heliospheric current sheet here. This is a ground-based eclipse image, and then the PFSS of that time period. Pseudostreamer, current sheet, and also, I'm going to show you later, this is a complex S-web, separatrix web structure, which means that there are lots of places all over the sun where magnetic reconnection could be occurring. The question is it occurring? So I'm going to show you both remote evidence and in situ evidence that actually all three of these locations have magnetic reconnection injecting transient plasma. We heard yesterday a talk by Ben Lynch about the fact that even though these are all places where magnetic reconnection occurs, the magnetic topology is quite different at the current sheet versus the pseudostreamer. And so the details will be different, but still it's the same basic process of magnetic reconnection at these locations. Okay, I just want to stress that what we're trying to do here is match up in situ observations with remote observations. That is not an easy thing to do, especially out at 1AU. Of course, that's what Parker Solar Probe and Solar Orbiter are going to be able to enable for us. We've had success doing this on a large scale with big things like CMEs and CIRs, but we've struggled on this smaller scale, these mesoscales. And by mesoscales, I mean tens of minutes up to a few hours, hundreds of megameters. These are small compared to the current imaging resolution, but they are large compared to turbulence. So these are large compared to the inertial range, at least out to 1AU. They are also large compared to Earth's magnetosphere. That is important from a space weather perspective. Even though these are small in the images, they're big compared to Earth's magnetosphere. They totally engulf it, and I'm going to come back to that point at the end. All right, so again, this is the time period that we're going to study. Just this general configuration of the sun is what to keep in mind. Here is a zoom in of that pseudostreamer up here. This is the current sheet down here. This is a high 1 image during that time period. This is specially processed high 1 data, though, by Craig DeForest. It's up on the public StereoSTECI webpage. Again, I want to stress we're really pushing the limitations of the instrumentation because of the sensitivity of the instruments. It can be difficult to see these. This box right here is a zoom. This box right here is a zoom in of the pseudostreamer right here. You can see all of the substructure coming off of these rays of the pseudostreamer. It certainly looks like this pseudostreamer also is transiently injecting plasma structure. And in fact, if we watch these rays as a function of time, if we take an intensity slice and then stack those up as a function of time, so these are intensity slices this way, and then as a function of time up, you can see these are kind of like the JMAPs. You have these transient releases of plasma going on all of these rays, transient injections of plasma that show up as density enhancement. So the pseudostreamer is not emitting steady solar wind. There is all of this transient structure being injected. Okay. Oh, and they're going at the slow solar wind speed. That's important. Now, what is it that our in situ instruments are seeing? At L1, we had John Linker in Predictive Sciences do a high-resolution map of what L1 was going to be flying through during this time period in general. And this shows a zoom in this little box right here. I'm going to show you the in situ data that goes with this box right here. What's important is these arcs here, those are complex S-web arcs. Those are locations where magnetic reconnection is highly likely to occur. Again, whether or not it does is still a question. I'm going to argue that it does occur, and that's what we're seeing signatures of in situ. Okay, this is a zoom out of in situ data at 1AU. This is about 14 days of data, about 2 weeks of data. This is the time period that that box mapped to, this time period where the proton density is highly variable, the alpha density is highly variable, the speed is pretty slow and pretty steady. We are in one sector, there's no crossing of the heliospheric current sheet, as indicated both in the magnetic field and in the heat flux. These are high-resolution ACE composition data that Sula pre-processed for us, because the standard data product is not quite at a high enough time resolution. But these are carbon and charge state that also show a lot of variability in this time period. So this is the time period that I'm going to focus in more on. Also, it is separated, well separated from the stream interface. Okay, so let's zoom in on that 2-day time period and focus a lot on the composition. Okay, here's the proton density, lots of structure in the proton density. Here are the alphas. There's a lot of structure in the alphas. Now remember, structure in the alphas, in the carbon, in the oxygen, in the charge state, which is what these bottom 3 panels are, is really important because you can only do that at the sun. So if we have compositional changes, that means we are crossing into new boundaries, new flux tubes that had a different heating history back at the sun. You can imagine coronal loops that had a different heating history, and we're tapping into one of them through reconnection, then we're tapping into a different one through reconnection. That's what the composition is telling us. Also notice, these lines that I've drawn here, I drew those based off of these compositional changes. So if you say that the boundaries of the flux tubes are defined by the compositional changes, because the composition is set way back in the corona, what's interesting is these boundaries line up with tangential rotations in the magnetic field, and 2 of them are heat flux dropouts. That requires complex magnetic topology, probably interchange reconnection, and Aleda Higginson is going to be talking in the next solar probe, Parker Solar Probe session about how the S-Web allows for complex conductivities to occur because of this S-Web. Okay. So, I think we are seeing evidence that in fact, this picture is what is filling the heliosphere. There's transient release of plasma that's creating the solar wind. Maybe not all the time, but that's what we're going to find out. I think the reason that this is happening is because magnetic fields store and then release energy, and that happens in a bursty, patchy way. The key, though, is we need high time resolution composition. So Justine, we need the alphas. Daniel, we need high time resolution composition, carbon, charge states, FIPS, all that stuff. All right? We also need high time and spatial resolution imaging. The modeling also is so important for interpreting what it is that we're seeing, it really matching the images with what we're flying through in situ. We're really pushing the imaging limits. Craig's going to talk about that next. There's SMEX that was selected for a phase A study called PUNCH, which is to look globally at the heliosphere in white light so that we can see not just if these structures are being created. The answer is yes, they are being created. But the question is how often, how much of the heliosphere do they really see? I think PUNCH is going to be a key to get the global context and how often, whereas, as we said, Parker Solar Probe and Solar Orbiter are really encounter missions. Okay, there's one final point I want to make. These mesoscale structures, they're happening all the time, I argue. They create the ground state of space weather. They create the space weather when there are no CMEs, no big CIRs. Still, there is space weather going on. That's what this movie shows. This movie shows a series of these flux tubes with enhanced density passing the magnetosphere. So even though they are small, they're constantly there, even when you thought there was no big CMEs, no big space weather. And so that is important because small things can do big damage. So I Googled that phrase. These were some of the images that come up: small carpenter ants, small leaks, small dogs, small hail. These are my small kids making big messes. Because of the cumulative nature, the fact that these are always there, these structures that come from the sun, they impact Earth's magnetosphere and all of the terrestrial planets. They have a big cumulative effect, and they really form the ground state of our space weather. Thank you.
Thank you. Questions for Nikki? Leon?
When you talk about Heliosphere, basically there is no reconnection at the top. So these blobs that you see could be also waves. And I want to make another prediction. There are going to be lots of waves in this.
Yeah, this does not preclude waves. This just says, I think magnetic reconnection is a big driver. Actually, Ben's talk yesterday, Ben and Aleda talked about there is magnetic reconnection at pseudostreamers all across the S-web. It looks different, though, than the heliospheric current sheet. It's not helmet streamer tip reconnection, it's interchange reconnection.
Other questions? Simon?
Nikki, I like your point that these mesoscale structures are very important for the day-to-day sort of space weather aspects, but are they captured at all in any of the models that we use for?
No, they are not.
It's very important. Jim?
Just a comment. So the NASA instrument, the HIS, is going to provide 30-second and 4-second composition information.
Awesome.
Is that good enough for you?
That
Are
is
those
good
the
enough.
skills?
Yep,
Yes.
that's
Okay.
perfect. Great.
Great. Excellent. Any other questions? Wallace?
Nikki, you see the instability of the corona in every single eclipse image we've got. So it starts way low down, and there's so much turbulence and so much, blobbiness that it's naturally what you said makes perfect sense. It doesn't just come from extremes. I mean, it is mostly extremes.
It's everywhere. Highly dynamic system. Yes. Yep.
All right, let's thank our speaker again. And next up is Dr. Craig DeForest talking about mapping that territory, the remote sensing, and expectations for Parker Solar Probe.
Thank you. How do I control this thing right here? Oh, that one. Oh, there we go. Oh, we're losing control already. Okay, so mapping the territory. Famously, we're going to fly through the outer corona with Parker Solar Probe. Let's see, this is a LASCO sequence showing the outer corona. That's about the size of the constellation Orion. You've seen lots of these perihelion pass movies. I just want to stress, this is sort of the deep field corona as we saw it, in the late 1990s. And the big result from LASCO was that the corona really extends, well, there are a lot of big results, but this one was that the corona extends out as far as you can see in this field. And so that tells you that Solar Probe will have something to fly through. But at the time that Solar Probe was being designed, nobody really knew where the alphane surface or the beta equals 1 surface were. There was no easy way to measure them, and it was sort of the missing boundary in the heliosphere. There were models, but no direct measurements. That's changed. So we can go after these things now. Using stereo, we've recently been able to drill in deeply enough to see the transition at the outer edge of the corona where the dynamics changes from what we might call a coronal plasma to what we might call a young solar wind plasma. This is where the striae, those radial stripes that any 5-year-old can draw, that's their end. They break up, and it's about between 20 and 80 solar radii from the sun. So the corona does just fade out, just farther out. That's a symptom of the fact that the solar wind is exceeded, the beta parameters exceeded unity, and so hydrodynamics is starting to drive the show and break up the radial structures that are formed by the magnetic field farther down. So we know that Parker Solar Probe will fly inside the beta equals 1 area here into the corona itself. The other important surface is the alphane surface, where the plasma becomes causally disconnected from the sun in the MHD approximation. And that's where the wave speed no longer exceeds the bulk speed, and so even inbound waves are ducted outwards. You can't actually go after that with remote sensing with LASCO. It just doesn't have the dynamic range to do it. So you have to go a little farther in to stereo core 2. And in 2014, we did that. We cleaned up some synoptic data from core 2, put it in radial coordinates, and used Fourier analysis to separate inbound and outbound moving features. The idea is if you're inside the Alphane surface, you ought to see features moving inward through the corona. Outside the Alphane surface in the solar wind, all the characteristics move out. There should be no inbound features. So, turning that plot or that movie sideways, now time is running right to left, or left to right. On the bottom, you can see outbound features. On the top, you can see inbound features. We were able to show that, in fact, in most of the corona, the Alphane surface is outside of 15 solar radii. Even in the coronal holes, we could measure that it was outside of 12.5, maybe 13 solar radii. But above that, we ran into a noise floor with these measurements, and so we couldn't go all the way out to the limit of the field of view. At the time, we thought that these were waves moving inbound, but Anna Tenerani and Marco Velli quickly set that straight and pointed out that this curvature of this characteristic speed curve is consistent with inbound jets rather than with inbound waves. That's okay. If the jets aren't shocking, they're still going slower than the wave speed, so we still have located the Alphane surfaces outside of that region. And in some ways, the jets are more interesting because it indicates that there is reconnection going on even in the far outer corona to create these jets moving back in. And that hints at some very complex dynamics, which hopefully we'll probe with probe. So, trying to measure a little bit better what's going on in this region, we took 3 days of campaign data with Core 2. This is, again, back in 2014. Angelos Verlitis really worked hard to make this happen, and this is what we have. The very first thing that you can see looking at these data is that the corona is much more detailed than in the synoptic data. And there's a little aside here. There's an interplay between noise and spatial resolution. No coronagraph to date has achieved its optical resolution. And the reason is, as you get smaller, the noise level compared, or as features get smaller, the noise level compared to the feature increases. If you've worked with images and done any smoothing or blurring of your image to reduce the noise, you know what I'm talking about. So with these deep field exposures, we were able to drill in and effectively increase the spatial resolution of the instrument. What you see is the corona has a lot more structure in it. So let's explore that structure a little bit. This is in polar coordinates and cleaned up a little bit more and radial filtered. You can see that there are, well, radial structures. There are also these various mesoscale blobs moving out. That's what Nikki Viall just talked about. And that as we drill in more, really seem to make up more and more of the flow. Now, watch closely at the screen. You're going to see this is what we were able to achieve with this special campaign. After filtering and a new process of co-moving averaging, we're able to get here. Unfortunately, it never looks as good on the screen as it does on the monitor. But we're able to drill in to where we can see that every single pixel there is part of a narrow feature. The outer corona, which I've always thought of as relatively smooth, is in fact every bit as complicated as the EUV corona. You can see it on the screen in the form of the wood grain texture, but the smallest features we're seeing here are just 2 core 2 pixels across. So we're essentially achieving the optical resolution of the instrument. We could probably drill a little bit farther, but not more than a factor of 2. The brightness contrast in these smallest features is about 5 to 10% of the K corona, which, because they're so small, means that there's a huge density contrast. So the density contrast in the outer corona is a factor of 10 in these smallest features. And that's really big news because it means that the outer corona really is not smooth. It really is all intermittent, whether horizontally or vertically. If we drill even farther, after doing the noise reduction, we can temporarily unsharp mask. I'm sorry for the jumpiness here. There are a lot of different optical flow rates that you can see in the corona. You can see that there are small features moving out everywhere in the corona. Now, we can use that to measure the flow speed remotely, and in fact, we intend to do that. Moreover, we can measure that there are multiple things along the line of sight. We can use the different flow speeds to disambiguate structures. If we had the ability to image with polarization, we could back out this structure in 3D. And so again, the reason this is jumping is it was pretty smooth before I MPEGified it so it would fit into a presentation. The different optical flow rates confuse the MPEG algorithm, and that's making it jump. So let's see, that's outflow. We can measure the various flow speeds. We can go and measure inflow, so repeating the Alfvén surface analysis with this deeper exposure sequence, you can see that there are lots and lots of inbound features. The top part shows only small features here. The lower panel shows the entire range of spatial scales coming inbound. And so once again, we can locate the Alfvén surfaces outside of this field of view. There's a paper and work with the same author list that we hope to get out in the next few months. Just because you have to be careful with these measurements, we also did a shuffling test. So if you look at the bottom panel here, the frames have been shuffled by up to 5 positions in the time sequence just to randomize them. And it's a good null test. It shows that the pattern is strongly attenuated by the shuffling process, and we're not producing any new inbound features. So that's a good null test. And it shows that yes, in fact, we are seeing inbound features in the Alfvén surfaces outside our field of view here. With all this great analysis we're able to do with these instruments, it's important to point out the limits of this kind of analysis with current instrumentation. That's the top of Core 2 and the bottom of High 1. And you can see stereo achieved its goal. Secchi demonstrated very well, let's start that again, that features that start in the corona propagate out into the heliosphere. It's not the whole story. We've been able to show with comets and with the High 1 analysis that, in fact, there's a lot of turbulence in the flow. So what we see at the Earth is almost certainly a mix of these fine-scale structures that Nikki Viall just pointed out and turbulent eddies that form en route. The problem is, right at the most interesting place where these two critical surfaces are, is right at the boundary of the instruments. And that's okay. The instruments were set the way they were because they were going after something different, which is the large-scale space weather. But now that we're drilling into the fundamental structure of the young solar wind, it's frustrating because the exposure times are different, the instrument characteristics are slightly different, and so we can't really make good measurements of how the wind changes in this region without separating them from the existing instruments. So, in summary, we can and have imaged the transition from the corona to the solar wind. We know that Parker Solar Probe will fly through both of the major dynamical surfaces, the beta equals 1 and the Alfvén surface. We know that outbound jets and really strong structure in the outer corona is every bit as complicated there and every bit as important there as farther in the UV corona. The density can vary by at least 10x on scales below 20 megameters. So that's order of less than a couple of minutes I guess a few seconds of solar probe flight. We need better measurements. We need still higher sensitivity to drill in and understand this fine scale structure. Polarization would be great because it would let us sort out these structures in 3D. We need a wide and continuous field of view to capture the transition. I would be remiss if I didn't mention that, in fact, we're working on that. Thanks.
All right, Justin.
Frank, really cool stuff. Question, when I think of beta classically, and I look at 1AU, beta is about 0.8 on average. So it hasn't quite gotten up to unity yet. And when I hear about the corona, I hear, oh, beta is small. So I don't think that there's a beta equals 1 transition between 1AU and the corona. So would you be okay with like a beta equals 0.1? Like there's some, fast mode waves aren't important anymore, transition at some value of beta, not necessarily 1.
That's a good point. That I really should have said beta twiddle 1 rather than beta equals 1. Once it becomes close to unity, then all kinds of things can happen that it can't at 10 to the minus 4. Yeah.
One more question, then we're going to have to move on. Jim.
So you're going to have to do a spatial power spectrum analysis to see if this relates in some way to turbulence?
Yes, see DeForest et al. 2018 in press, or in work.
Perfect. Well, thank you again, Craig. Next up, we have Nick Arge, Dr. Nick Arge, talking about the WSA model and predictions for...
How's the...
sorry, I have to give you the right advancer.
Okay. Just up and down arrows.
Yes.
Okay, thank you very much. Basically 3 things I want to try to get across today. One is I'll just do a very brief updates, reviews of WSA and the ADAPT models. Since I've shown that several times, that'll be pretty quick. And then I'm going to show you some results using HMI magnetograms, both line of sight and vector, with and without a far side active region included, and how that can really make a big difference in our ability to predict the solar wind and the coronal structure. And finally, I'll provide a methodology for selecting the best input maps for the models. And I'll explain more about that, obviously, as I go. So ADAPT is a flux transport model, and there's several out there. This is a 4.5 month run of ADAPT during the 2010 period, so I'll be focusing on these data right here. Again, I'd like to acknowledge Stanford for providing these data. But right here, this is, so it's a data summative model, and this is a time evolution over 4 months. These data are key drivers to all coronal, virtually all coronal and solar wind models. So ADAPT, as I've talked before, it's a flux transport model, and it's a little bit more than that. It is truly data assimilative, and so it uses various levels of data assimilation, but it always takes into account the model uncertainty and the data uncertainty. And so it's if you want to see in detail Hickman et al., they use at least local ensemble transform Kalman filtering, so it's very elaborate. The main thing I want to get across here is, there's a pointer right here, I believe, is it adapts in an ensemble model. And so what it does right here, this is not a movie in time of the ADAPT solutions of the magnetic field, but it's actually a sequence of the 12 possibilities at a given moment in time of what the sun could look like. And so right here is where data were recently incorporated or assimilated. So you see less variation, but on the far side here, you see that there's quite a bit of fluctuations there. That's the model trying to estimate what could possibly happen. Also, that's true at the poles. And this can actually produce quite a bit of differences in solutions. Now, what the ensemble is supposed to do is represent as well as possible the true uncertainty, and if we're doing it right, it will do that. WSA, which I'm sure you've heard about many times before, this is a simple potential field type model. This actually includes a current sheet, so it gets the upper coronal structure a little more accurately. It runs very quickly. So the input would be input maps like ADAPT or other input. The output, what you get is the global coronal field, actually out to infinity, but we usually use it between 1 and 5 to 21.5 solar radii, depending on which model it then is fed into. But the output is the coronal magnetic field, and so at this outer boundary you get this global solution. This is negative polarity, so it's in towards the sun, and positive polarity out, away from the sun. And using empirical relationships, you can get the solar wind speed in this outer boundary. And these two parameters are then fed into simple 1D kinetic models, or kinematic models rather, or advanced MHD models like LFM Helio or Enlil and so forth. Here I only show the open field lines, but if you trace those down, you basically are down at 1 AU. So you have this map here, so you have that, but converted from negatives to positives, just polarity, and then the field lines traced down outline the coronal holes, or the sources of most of the solar wind. Okay. So this is an example, just a random example in 2007, but it highlights some important points. These are the 12 ADAPT realizations. So what you're seeing is it's one moment in time, June 21st is the input. In this case, we're assuming that the sun doesn't change over the rotation, this full Carrington rotation. But what I'm trying to highlight is here's 12 different possible adapt input maps for June 21st. And then you can see how the corona and the solar wind's changing. And so if you sort of, maybe jumping the gun here, but if you look right here, this is the sub-Earth point. That's the line connecting the sun to the Earth over time. You can see that one case we're above the current sheet, other cases below. It's wagging back and forth. And you'll actually see right here that depending on which one of the ensemble members you use, it's saying it's either the solar wind's coming from down here or up here. And if you look at the actual solar wind observations, this is interplanetary magnetic field polarity. So this is the black line's the polarity, plus is outward, negatives inward. The blue are the model predictions. You see sometimes we're really wrong. So this region right here is from here. And you see in some cases we're getting okay, other cases we're getting it, we're completely missing it. And if you just follow through, this is the solar wind speed. There we got a really good solution. Okay, other cases we're completely missing it. And so just very subtle changes can actually tell you, you're either completely, you're capturing it right or you're not. And so what ADAPT can do, combined with WSA, is, for instance, with Solar Orbiter, is to actually provide a forecast of the most likely position or where the sun is, where the spacecraft is magnetically connected, or the Earth or solar probe or orbiter is connected days in advance, so for pointing purposes. Also, what it can do is actually say, this particular realization coming up here is right, not that, but right there. That's probably the best input map to use for your global modeling. So if you're trying to interpret your data and you need to have a global solution of the corona and solar wind, you'll want to use that input map. You'll see here that while there's a lot of uncertainty here, later on there's very little uncertainty of where one should be pointing. And so this is how this combined model can help with mission support of, for instance, Solar Orbiter. So I actually say that right there, so I can move on. But it does provide pointing and uncertainty. Yesterday there was some talk about observing the polar fields, and I just felt compelled that I should do this. One of the things that we have problems with is we don't see the poles well. Sometimes we don't see them at all. It turns out the global models, doesn't matter if it's potential or MHD, they're extremely sensitive to the polar fields. And so we really need to observe those as if possible. And of course, fortunately, the Solar Orbiter will be able to do that. And so this is something I think could actually help us quite a bit. The other limitation with some of these models is the fact that we can't see the far side of the sun directly with magnetographs until later with Solar Orbiter. And part of what I'm going to show you is that if you don't include far side magnetic fields, you can sometimes do very poorly at predicting this coronal solution in solar wind. And so this is a composite of magnetogram this is from NSO, and then also using helioseismology, they can detect far side active regions. And so this is a far side active region, and so using helioseismology, you can get the position and its uncertainty, sort of basically the difference in size and shape. You can get the magnetic field strength given a correlation between the phase lag and the sound wave signals that propagate through the sun and the magnetic field. There's this correlation here, along with an uncertainty. And then Lisa Upton talked about using a similar approach where you use Hale's law and Joy's law to get the polarity and the tilt estimate. If you're sophisticated, you can actually include, you can actually create an ensemble of solutions of this far side active region. And so you might have an ensemble of ensembles of solutions. But those combined, you can then insert those into the far side. And I'm going to give you a particular case where we actually do that. This is work that Carl Henne has done, and then I've used that. And, but the nice thing is that Solar Orbiter will be looking at the far side. So I've said this a couple times, but I really encourage to get as much far side observations as possible. It will help us know how well to do this and how well we need to know how to do this, and how much we could actually play off the helioseismology. Maybe we just need to know well enough, and so then, but having direct observations along with the helioseismic signal should be able to help us learn more about how to do this right. So now I'm moving to some solutions using HMI in WSA. This is for the the June-July period in 2010. There was a far side active region virtually directly on the far side of the sun, almost 180 degrees away. And I'm going to show you cases where we don't include it, where we do include it, and how that makes a difference. So here's a photospheric field. This is without this far side active region in there. And this right here, compared to the previous map, this is just one day of a sequence of 28 days of input that we put into WSA. So we're actually updating every day now. This is the IMF, and you see overall we do okay. Here we're missing this region right here. This is the polarity. We're not getting that polarity right. We may be jumping in here a little bit down here a little bit too soon. Overall, you can say we're getting the stream structure okay. Now let's look at it with the far side active region inserted. You can see here that maybe we're doing here a little better. And these are all line of sight, I should point out. And we're still getting the stream structure. Maybe we're getting right here a little better now more often. Before we were missing. Now we're doing vector. And you can see that we're capturing this stream structure right here a little bit better, the IMF polarity, but not perfectly. And the velocity is okay. Now we've included the far side active region. And if you watch, we're now capturing the structure very well. And so this region here is this, and then down here, and then that is that, and then down there. So really, we could say definitively we're going here, here, up to here, and down here. And there's a few of these realizations that actually capture that structure. So the goal here is just to show that getting the boundary conditions right helps a lot. So then I tried it that was at ACE, or at Earth. So now I did it with solar stereo B, and I did A, but I only have so much time, so I'll just focus on B. So stereo B was right here. And this is what without the active region. You can see that we're getting the solar wind pretty well, but we're really over-predicting here. And that's just this large coronal hole extension. And we're really just predicting a much larger stream than is there. When we actually include the far side active region, though, this is greatly reduced, and we're actually close, maybe not perfect, but we're actually capturing the structure more realistically. And it's just, again, to show you the sensitivity that the models have to, and the importance of including all these data. And if we were to had an ensemble of solutions there, we probably could fit that well. And then the last thing I want to talk about is every one of these runs that I showed can literally be 400 runs. So the model runs quickly, but you get overwhelmed by numbers. And so the thing with it is fortunately, so WSA adapts good because it runs so quickly. You can go through, plow through a whole lot and select the best maps to use into more advanced models. And so over the summer, we had a student who actually developed a methodology, we developed methodology for selecting the realizations of ADAPT that provide the best solution. And it's a ratio of the correct, so this metric is the percent correct IMF polarity, how much of the polarity is correct, right, divided by the RMS velocity residual, basically the difference between observations and predictions. It's a nice metric because if you're 100% right in polarity, then everything depends on how close you get. Smaller the differences, the higher that number. The bigger the differences in velocity, the bigger that, the worse you do. But if you get the IMF polarity wrong and you get the velocities right, you're still wrong. Because it's like if your IMF is coming from the wrong region, it's wrong. And so that's a nice filter there. Is IMF's the first filter, velocity is the next filter. And what you see here, let me just wrap up here, is that over in 2009, we saw that there's periods where one realization, this is realizations 1 through 12, and there's periods where one realization will stand out for weeks at a time, months at a time, and so that gives us confidence that it's just not randomly jumping around, but we can actually pick that out. And so let me just stop here and summarize that basically I've talked about ADAPT, talked about that the solar wind, getting the magnetic field right is very important, getting far side is important. It looks like having vector BR in there is a big improvement along with far side. And we can, a lot of this work will greatly benefit the Parker Solar Probe and Orbiter because it can provide predictions about exactly what's where to point in advance, what's the most likely source region of the solar wind. It also can select the best input map, so when you're doing modeling and studying your results, you'll be able to use a global solution that has the best, provides the most realistic magnetic, global magnetic coronal field solution, so forth. And we have a method now that's for forecasting purposes and practical reasons, and we can objectively select the best input data. Thanks.
Time for one quick question while Samantha comes up, or our next speaker comes up. Anybody? Marco.
If you had to choose between far side and polar.
Pardon?
If you had to choose between far side and polar.
That's
And you only had, you could only choose one.
I picked polar because we can use helioseismology to do that, so I would pick polar.
Good answer, good answer. Thank you, Nick. Next up is Dr. Samantha Wallace to talk to us about the magnetic expansion factors in the solar wind.
I don't have my PhD yet, but that's okay.
It's all good.
So, thanks. So what is the magnetic expansion factor? It measures the rate at which an Earth-directed flux tube expands in cross-section between the photosphere and the solar surface as compared with a purely radial 1/r² expansion. So you can see what that looks like in the diagram where the flux tube is expanding from 1 to 2.5 solar radii. Expansion factor was defined by Wang and Scheele in 1990 by the equation at the top, denoted by F sub s. And based on the original definition, the first term would be 1/2.5 whole quantity squared, and the numerator of the second term would be the magnetic field strength at point P on the photosphere, and the denominator the magnetic field strength at point P on the solar surface. So in 1990, Wang and Scheele derived solar wind speed empirically based solely on expansion factor represented by the bottom equation, and their work was later theorized in 1996. They also demonstrated that expansion factor and solar wind speed are inversely related. So if you imagine this as a polar coronal hole, the field lines at the center are nearly radial and have low expansion factors and fast solar wind emerging. And the opposite is true at coronal hole boundaries, where these field lines have undergone much more expansion, have high expansion factors, and solar wind emerging from these regions that typically has slow speeds. So the WS model has evolved greatly over the past 25 plus years into what is now known as the Wang, Scheele, Arge, or WSA model, which you just heard about in the previous talk. So I won't really get into the top portion of this slide, but on the bottom we have the current solar wind velocity relation, which has also evolved greatly and is now not only a function of expansion factor, but also theta sub b, which represents the minimum angular distance that an open field foot point lies from the coronal hole boundary. So there's a lot of recent studies that question the physical role played by expansion factor inside pseudostreamers. A pseudostreamer is when you have two coronal holes of the same polarity that are near enough to one another to limit the field line expansion between them. So if you look at this WSA output for the derived coronal holes for Carrington rotation 2060, you have the solar wind velocity and color scale, and the background gray scale represents magnetic polarity. The black arrow is pointing to two coronal holes that could potentially form a pseudostreamer. And if you look closer at the magnetic field structure that you typically see, you have fast wind emerging from coronal hole centers that have undergone very little expansion. You have slower wind emerging at the boundaries where you see more expansion. However, at the pseudostreamer cusp, these field lines essentially repel each other, and in many cases do not expand as much. So if you were to use the original Wang and Scheele prescription, if you have low expansion factor, it would yield fast wind at the pseudostreamer cusp. So this potentially creates a problem for the expansion factor model, since coronal hole boundaries typically are sources of solar wind that have slow speeds. So there have been several case studies featuring between 1 and 3 pseudostreamers that I don't have time to get into all the details, but they compare expansion factor and solar wind speed. Some of which that argue if you derive solar wind based entirely on expansion factor, you produce fast wind at pseudostreamer cusps when the observations for those time periods suggest the solar wind was slow. And then there's other studies that in some way support this expansion factor solar wind speed inverse relationship, and say that you really need to consider the entire magnetic field geometry. And when you do, you can have pseudostreamers that tend to expand more before they reconverge at what's called the X point, shown indicated by the blue arrow. And when that happens, you can have higher expansion factors and slower wind emerging. And then you can also have pseudostreamers that are narrow fan-like structures that can have lower expansion factors and solar wind speeds of approximately 600 kilometers per second. So despite all this prior work, it's unclear whether expansion factor plays a physical role in solar wind acceleration in the open field corona or serves as a proxy that distinguishes between fast and slow wind. So the focus of this project is to contribute to resolving the same question as these other case studies, but via a statistical analysis of a large sampling of pseudostreamers that occur at various portions of the solar cycle. So not only, we're currently looking at coronal hole boundaries, but future work, we plan to look deep for those field lines deep inside coronal holes to answer this question. So to accomplish the first half of the project, we need to identify periods where we can say with a high level of confidence that spacecraft are magnetically connected to pseudostreamers, and then use the WSA model to drive the expansion factors. So we began by looking through WSA output for the past 10 years. So here's the derived coronal holes for Carrington rotation 2062 from roughly October to November 2007. And we have the white crosshairs, so it's difficult to see, that are cutting through the center of this map represent where the spacecraft, in this case ACE, is located relative to the solar surface. And then the black lines represent those field lines that are magnetically connected to the spacecraft. So here is a pseudostreamer where you have the field lines at the boundary of these coronal holes connecting to the spacecraft. And the solar wind that emerged from this region left the sun on November 3rd. And so WSA actually tracks the parcels of solar wind that leave pseudostreamers and determines their arrival time at the specified spacecraft. So at that arrival time, we want to make sure that the model-derived and spacecraft-observed solar wind speeds are in reasonably good agreement so that we can ensure that the spacecraft is in fact sampling that solar wind that emerged from the pseudostreamer. So we can, this is just one of our preliminary checks, we can look at this plot from WSA where you have the model-derived solar wind speed in blue and the spacecraft observed in black. And so for that rough 5-day period where we estimate that that's the travel time for this parcel of solar wind to reach the spacecraft, the two solar wind speeds are in pretty good agreement. So once we think that we're identifying a pseudostreamer, we can use a new feature of WSA 4.0 to create a 3D rendering of the global magnetic field configuration for these features. So plotted here are triads of open magnetic field lines, where the ones in the middle are the ones that are connected to ACE, and also plotted are those positioned half a grid cell above and below what are called the subsatellite points. So those field lines that you see in the middle of this 3D rendering correspond directly to those crosshairs that you see in the 2D coronal hole maps. So essentially this is the perspective of the spacecraft. You can see this is quite a large structure, and there are several field lines that are connected to ACE. And you can also see that it's a pseudostreamer, like the tops of these triads are connecting up at the poles, and the bottom of the triad, those field lines are connecting down to a mid-latitude coronal hole. And so this is the same pseudostreamer from the side. You can see these field lines are expanding before reconverging at the X point. So once we've identified a pseudostreamer, we can use the model to obtain the photospheric latitude and longitude of these field lines. And then using this information, we can track this exact parcel of solar wind that left the pseudostreamer and obtain the date and arrival time of solar wind at the specified spacecraft. So here's a plot of the solar wind speed on one vertical axis, an expansion factor on the other for the Carrington rotation we've been talking about. The spacecraft solar wind speeds are in red, and we want to compare those to the model-derived expansion factors. But we're going to use the model-derived solar wind speed, plotted in green, to determine the arrival time of that parcel of solar wind at the spacecraft. So this parcel of solar wind that left the pseudostreamer cusp, according to the model, arrived at the spacecraft on November 8th at noon. So in this gray region, the blue dots that you see are actually the expansion factors for the exact field lines that form the pseudostreamer. And within plus or minus half a day of that time period, the spacecraft observed and model-derived solar wind speeds are in pretty good agreement. So we're pretty confident that the spacecraft was in fact sampling the wind that left that pseudostreamer. So for this particular case, the solar wind speed is relatively low, between 270 and 300 kilometers per second. The expansion factors are also pretty low to moderate, between 7 and about 20. But this is just for one case, so we've been able to do this for 9 different cases so far where ACE is magnetically connected to a pseudostreamer. So we can plot these 9 cases. So we have the points are each their individual pseudostreamers, and they represent the average ACE observed solar wind speed versus the average expansion factor. And the horizontal error bars represent the standard deviation and expansion factor for all of the field lines forming the pseudostreamer. And the vertical error bars represent the observed solar wind speed standard deviation within plus or minus half a day of the pseudostreamer cusp solar wind arrival at the spacecraft. So first, our preliminary results are consistent with prior work in that the observed solar wind speed inside pseudostreamers is in fact slow, from about 500 kilometers per second or less, and the expansion factors are pretty low to moderate, between 5 and 25 or so. So at this point, if we were to naively to calculate the linear regression and plot the line of best fit, we would observe an inverse trend with a pretty low correlation coefficient. So, but if you were to see this one pseudostreamer as an outlier, you could redo this calculation and obtain the opposite trend with a bit stronger correlation coefficient. So the point is not that this particular plot is more reliable, it's just that at this point, adding or removing one pseudostreamer to these statistics significantly impacts the results. So we really need more cases to do better statistics. So just to conclude, I won't really go over everything, but at this point our results are statistically insignificant due to our small sample size. We plan to extend our study using stereo A and B to obtain roughly 30 or 40 cases where spacecraft are magnetically connected to pseudostreamers. We also want to use these 3 spacecraft to sample through the same pseudostreamer within a period of roughly half a Carrington rotation or so. We also plan to incorporate other things such as charge state ratios and so forth into our study. And also, we could ask, should we even expect a correlation between expansion factor and solar wind speed at the boundaries of coronal holes anyways? At the pseudostreamer cusp, or the outermost coronal hole boundary, these field lines are constantly opening and closing. And so the acceleration mechanisms between the open field corona and closed field corona are very likely entirely different mechanisms. So to really investigate whether expansion factor does play a physical role in solar wind acceleration, we need to be looking along continuously open magnetic field lines. We plan to do that in future work, looking deep inside coronal holes using Ulysses observations at the poles. And lastly, I just want to say it's possible that the solar wind emerging from specifically the pseudostreamer cusps is fast, very close to the sun, where we have the primordial stages of solar wind. However, if the surrounding wind is entirely slow, by the time all of that wind would evolve out and reach 1 AU, you would never resolve those details. I say that more to say that with Parker Solar Probe, we'll be able to observe the solar wind in its primordial state, close to the sun, pre-evolution, and it will undoubtedly be a game changer in separating out these acceleration mechanisms between the closed and open field corona. Thank you.
We have time for one question before we have to close the session. Marco.
Thanks. Very interesting. So I think that what you last said is probably the most relevant thing, and so the question is, you should count on it in things like composition or things like that.
Yeah.
To discriminate between pseudostreamers continuously also emitting wind from the sort of pre-confined regions and mixing that wind with wind coming from open field lines, sort of more steady state, if you like.
Yes.
Probably leads to it. You have some indication that there are 2 populations there.
Mm-hmm.
You show those like scattered everywhere. You do get the feeling that you have a nice inverse correlation and then another population of wind, which is actually slightly.
Yes. The plan is to instead extend our sample size and then to look into those other things, including magnetic field configuration similar to your work. Yeah.
So let's thank our speaker again, and I'm sure we can catch up at the break with her. Thank you to all of our speakers, and thank you for attending. This session will continue at 10:20, so we have a break between now and 10:20. So we'll see you back then.